Hello. So, I was thinking about this thing lights, LEDs, and volts and amps. So, I don't really know why, but the definition and what people tell me is that what volts and amps mean don't really seem to make sense to me a lot. Because they're like, it's the force, volts are the force, right? Instead of like force is mass, acceleration squared. And it's like, I'm very sure that you're not accelerating an electron through something. Yeah, I mean that's a particle accelerator. It's a subatomic particle accelerator. So very sure that's not a thing. I'm not saying you can't. You know what I mean? I'm not saying that because it's still possible to do that. But amps makes a lot more sense because it's just more electrons going through, which that makes a lot more sense, right? It's like a wave versus a squirt gun, except that's not really quite the case. Like if a squirt gun was like a water cutter, like right. Except this is where the analogy falls apart for a lot of people, because of course we're talking about subatomic particles that all have quantum physics typically going on. So I like the basic example, but it falls apart for me, and I have a hard time understanding it. So I ended up describing it to myself as, think of it like a Newton's cradle, or it tries to do something and then it produces a wave, right? And then sometimes that wave gets clumped up because there's already a lot of movement and electrons going on. What that means is it becomes more like a big, huge, instead of one single electron, it's a bigger, larger group. But it all acts in step with one, right? As one single pulse. Think like a dot and a dash. So it's like, this is the dot, okay? And amps are dashes. So big, this is a dot, this is a dash, okay? Right? And that's a way for me to conceptualize it as a pressure wave, because it's a pressure wave, right? Now, a better way to imagine it for those volts versus amps here, because most people know about Tesla coils, right? And the way that we usually increase volts is because we have an electromagnetic field that collapses into a wound coil, right? There's a lot of little winds in this little tiny wire on this little spindle, okay? As the field collapses towards the spindle, that absorbs itself into the cable, the material that's there, right? Now, that tends to mean that the electrons then move a particular way in their orbit, and they all start trying to head towards the least resistive path, okay? Then they become multiple chunks that then add themselves together inside of a rounded single kind of like state that is expressing its own field as electrons move through it. That's electromagnetic, okay? As that goes through, of course, then that interacts with another one and another one and another one, and becomes like it's a big cable. That big cable then acts as if it's one ginormous chunk of a dot, right? And so like all those little fields turn into a bunch of these chunks of dots that are trying to order themselves into one huge coil on there that then become one big huge dot. All right? But it sounds like it's amps, right? But imagine it like it's still this one single representation of one thing. Like the Newton's cradle, boom, as the pressure wave goes through. That kind of thing. So it's like boom, now it equals this kind of like idea of all of that field energy, because it's potential field energy effectively, sent as a dot, right? Now, because it's in a chunked manner, that's why it's a dot, versus a amp, which is more like a dash, duration, delta, versus dot, which is one single dot, boom, like a, drum beat, versus a boom, it's now a sine wave, versus a single blip impact, right? And that's what a volt is. So a volt is like this big informational thing of a dot that was hit this amount, whatever that is. Okay? And so that travels, and it goes to whatever. And depending on the volts and how you deliver those volts, which is the equivalent of sine wave, AC, DC, blah, 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 blah. Lots of words that don't really mean much to most of us. Okay, they really don't. People don't really grasp that. So think of it like I'm blowing air onto you, or I puffed air onto you, or I blew air on you, but I did it with a nice up and downward motion, wider, smaller, the right way, or I decided to puff it the right way, that kind of thing. That's all what AC and DC usually tends to mean. So, anyways, but the material that tends to make light, really just for us, and all intents and purposes, takes a given electron orbit and it puffs it out, and it has it come back in towards its orbit initially, where it started. Now the only way that works is because as the electron's trying to send information, it wants to go here. Well, it has to move all these other electrons out of the way, and that's called resistance. Okay, that's what Ohm's resistance is about. So electrons aren't extraordinarily heavy, and they're already moving anyway, so it becomes quite easy to do it. That's why it doesn't have a lot, usually, for certain materials. But some metallic ionic bond materials are extraordinarily strong, like they're quite close and they don't want to move much. Right? They're very good at where they're at. Right? Others, I can move, whatever. And that's the basis of why different materials have different resistances. So, now, got all that out of the way. This little Newton's cradle bump now has to send all this informational wave energy, which is the equivalent of, well, all these electrons need to all get in line, in step, and they have to communicate and go, hey, this wants to come here. It goes to this point where this, material is that's trying to effectively puff up its electrons and then, make something happen. Okay, cool, super, right? However, in order to do that, it has to do it somehow, some way, to where ultimately electrons along all the cable, along all the material, all of this, have to come in somehow, right? It's like in the line of what I'm doing. I have to eventually move to this point. I go up to the cash register or whatever, and I do my thing. Right? So this is what the light is that's going to be produced. But it's like, how does that happen? Right? So it produces a cloud, a virtual uncertain field of virtual electrons. Now, as electrons are orbiting, they tunnel around, and then they don't exist technically in that spot, right? But there's a spot of the lowest resistivity that exists as a positive to its negative, and so it tunnels and collapses back in to where that is at that point. We never know really where that is because it's hard to measure, right? However, what that means is it's a band of energy. That's why we call it tunneling. It's a barrier, but it's a band, and that's why we call them orbits, right? These are cloud orbital probability fields of where the positive energy could exist. Okay, the positive charge, right? Now, there's the only most likely and can only really be, and so of course it will tunnel to that spot, right? We just can't measure that very easily. However, because we sent this big field of potential existence of this electron, and everything has to get in line with knowing what's going on, the material goes, all right, so this is where it would end up, right? Not what we put in, because that stays at where it started. No, all of those other, but they're not. They're not going to do that, okay? I know this sounds weird, counterintuitive, but they didn't move ever, okay? This is the weirdest part. An electron moves out of its orbit a little bit and interacts with another electron's orbit, and it goes, it crushes it in, and it moves everything else around. So now we're at the material. It produces this weird, virtual potential negative charge, okay, field that is going to try and soak into any and wherever it might be of where the positive existence point of where it could collapse and tunnel back into its orbit can be. So that means the brand new negative field of charge then suddenly enters and collapses new electrons as to where they were going to tunnel, existing before. The ones that then tunneled, they exist as this negative field, but they can't go back there now, right? The new electrons exist there, right? That energy that was used to move something created new electrons, right? Except, to us, it wouldn't really be much of a difference. Who cares, right? So, moving on from that, the electrons that got tunneled into the energy barrier of negative charge, right? Well, that stays. Now, these electrons, where they could have ultimately been, should this potential field ultimately not existed, suddenly can't be there anymore because, well, there's a bunch of negative extra field energy, right? Negative charge. That puffs it out, and then it goes, oh, I will then head back towards my original point of existence, okay, in that field orbit for this material. But in order to do that, I have to tunnel the right way to produce a blowing off of heat in its mind, okay? Now, heat is relative. So it does a phase change to both its field energy and converts it and collapses it into a point. We call this a photon. It converts negative charge into a photon, right? That negative charge field collapses and it comes out relative to the speed and the energy and the distance that it travels, or could have because it's tunneling, to create a photon of a specific wavelength. Right? Now, different materials, different amounts of electron orbit and distance and heat, which is kind of what it does because it rocks the molecule and the element, where the nucleus goes, well, I was pretty lockstep where I was. It's pretty, low resistance, it's pretty much right here. And then this happened, and it kind of was right here briefly. And it was right here as that then made, photons. And then, it starts doing its, in no way, very consistent movement because, of course, they tunnel over here, they can be here, they can do it, so they get popped. And this is the nuclear force that creates this area of effect positive field, right? And so that got bigger and smaller in certain spots, and so it's moving around to try and effectively stay right where it could ultimately be lowest energy, right? This is what creates heat for all of us, okay? For our relative purposes, it suddenly started moving more, right? However, okay, it also bled off heat for us in the form of photons, which is great. The problem is, of course, we don't want heat, right? We don't want heat. That's not a good thing. And we want it to do it such that it's very efficient at converting its negative charge area and tunnel back to where its orbit is to more photons and less heat. Now, we don't really have a lot of ability to do that very well. I mean, these are subatomic particles and, on molecules on really small scales. They're not like our size in any way. So it's really hard to work on them, okay? So usually what that means is that when it tunnels, when it tried to effectively, go back to where it was, the same problem occurred. New electrons came in, and that's now there. And so it creates this consistent, well, I bled some of my energy, my orbit off into photon, right? And I reduced some of my energy heat, but I didn't really, as I've never really gotten back. So there's this big puffy cloud of constantly moving around negative charge field that's never really quite shrinking, and it's technically getting bigger until it kind of reaches its equilibrium. And it doesn't convert most of that negative charge back into any photons or electrons. Okay? Which is a problem, actually. That increases the movement of the nucleus of the atom, which is more and more heat. Okay? Now, that seems cool. Wow, right? Except if we were to deliver it correctly and pulse it the right way, which instead of pulsing, actually this one turns more into the amount of volt, the amount of amp that we see for that given material, and its negative charge, as it, of course, still tries to reach that equilibrium. So it's part of usually a molecule instead of an atom, right? But it's got a bunch of more around it, and so that charge will go into something else, and so it will always bleed its negative charge field energy into everywhere it can. It just happens to fill in the gaps effectively wherever it could have gone to. It does it the least resistive way. But that means it starts vibrating and moving very specifically in step to that initial and then the least, and we get the chaotic. It's very hard, ultimately, to calculate for that. And so it looks quite random, right? And it would be, because it's, of course, whatever the least resistive at any given point, and it's always moving against itself and anything else on the outside noise, people talking, microwaves on, fans over there going, whatever. You get it, right? So, what do? You get an analog chip, a simple silicon transistor analog chip, and you make a substrate that you place on for nano-sized to micron. We're looking for pins effectively, but as it goes to various spots of the material for the light emitting diode, which is usually what this is, that of course creates multiple small spots where you can input energy as that, well, in the form of that electricity, but it's not electricity, it's fields. But if you do that, that changes its resistivity and changes the amount of volts and amps needed, and allows for it to drain off into other areas and have the fields collapse and produce, effectively, less heat, less chaotic movement, and more photons. It becomes more efficient. Now, those pins have to be quite small, and they all have to head back towards the power delivery pins to the chip. So, what that means is they have to have the outbound chip power pins delivery, which is why it's analog. We're no longer going digital. They can only do, hey, I'm going to have this come in. No, that's however many volts, amps, whatever, right? That you happen to have for your country and power delivery. But, of course, that always changes, depending on heat, cool, other electromagnetic, what you're running in your home and your apartment and more. So that changes its amount, both the frequency and the total variation there within. And it's always happening very quickly at multiple spots. Now, we tend to not care that much about that, okay, because it means like nothing for us regular people. But for these things that are really small, it means a tremendous amount, actually. And so these pins that I talk about are much more like the pixels for cameras, okay? They're potentials. So once a potential is met and it needs something, it will then grab it, right? Otherwise, it'll take it from excess as it can drain back off into the potential and then use it, which modulates the power delivery from the chip into it to correctly make sure that it's always at its most efficient degree of negative charge field and energy placed in to make as much of the photons that they can ultimately make, and off of the modulation both of the input of energy, electricity in this instance, as it can effectively switch to any and all of the outbound power delivery pin sets, kind of like a power delivery for a regular CPU, but in this instance, this needs to be happening a lot faster and far, far more analog and designed specifically for the actual LEDs. So that's why there's a substrate pin for this to be connected to, right? That all helps that regular LED produce more light and form this is the reason why I was thinking about it, resonance that uses a self-correcting method. So like, if you get it really good at being able to be effectively resonated and moved just the right way, any outside noise of actual movement, not so much electromagnetic, as it would take energy, most likely, or put energy in, right? But to a degree, we might be able to do that. However, it just means that it self-corrects, and so it'll express more light off of that, right? As that improves the degree of the energy necessary for the tunneling band of energy gap, right? So like that's why I view it as a band gap, but it's not. It's an energy barrier in the quantum tunnel land, but I don't really care. It's a band gap energy. So once it has a degree of movement as it compresses, but also elongates, but also all that noisy noise stuff, because for all intents and purposes, we're talking about electromagnetic getting closer and further away. So it's an energy barrier. You know what I mean? Like that's all that is. But sound moving through anything is just the same thing. It's an electromagnetic energy barrier that's moving around. Same thing with electrons, through the cable. When you talk, it's the same thing. The only reason why that kinetic actually transfers to anything, same thing, basically. So, move on. But that changes band gap energy frequency and energy barrier to tunneling. It improves the amount of light emission, but it's very, very small. Okay? Very small. Which is fine. It wouldn't matter in any way to us. We're just using it as a self-corrective method to effectively make sure it doesn't get hotter. We don't want it to get hotter. We want it to be very, very still and be very efficient at making as much light as possible for little amounts of energy. Right? So, that's wonderful. In fact, if we set up the LEDs the right way, we're in lockstep as it's delivered, it starts to resonate and improve this efficiency towards the whole. It then creates its own self-corrective to the entire whole LED, which is the reason why I was thinking about it. That's a good thing to do. So, when you use that the right way, that in its own right could become an amazingly useful light bulb, right? It could also become a sensor and detector for movement or any of that, which we kind of use in a way. I don't really care about that. That's more for labs and, other people that would amplify the amount of light you see, because it would be so minimal we wouldn't notice or detect with our eyes any noticeable difference in light. If there is one, it would have to be some other, very specifically set up to increase that probability of you noticing the shift in total luminosity. Okay? But that is not why I was thinking about it. It's like, well, light is, hard to produce, but it's only because, we kind of do it wrong. We don't do it well. LEDs can be easily improved upon. In fact, most light bulbs could be too. And this increases the degree of efficiency, but also the reduction in total energy cost. And the production of it remains basically the same. We're talking about some vacuum sputtering, onto a given substrate, which the LED happens to be a part of, which improves the degree of potential types of, pin sets, as we can get into the nano sizes, and they can handle a large amount of volts, and that'll be fine, and the amount of amps that we need are delivered correctly. So it'll be fine. It's more to do about the fact that it hasn't really been done, as far as I'm aware. Now, instead of it becoming a style all its own of calculator, which would be pretty interesting, it would take a little bit more to do that. It just makes it more efficient at making, if you wanted to, light transmission through a fiber optic, and make it more error correcting, I suppose, to any given noise, which would become much more easily used as a quantum internet fiber optic, which would be amazing. Or transmissions on a style PCB that uses fiber optic and doesn't need that to effectively get noisy, so to speak. You know what I mean? They still get like the encrypted, I suppose, if you wanted to, but it's not really about that. It would turn more into like just straight, like huge amounts of bandwidth that you could run through the thing, especially if it was a conductive fiber optic. So that would help, because then as it gets detected, that improves the amount of electrical conductivity on the other side. It's light that then changes and modulates its given amount of frequency and voltage delivery, as that is information passed to a standard silicon-based transistor, which increases its outright bandwidth and throughput and speed and delivery and calculations. I bet you could probably make a silicon tube transistor with the right silicon deposition using sputtering techniques around a given fiber optic substrate. You know what I mean? Like, it's like, this is the glass or whatever, and it's basically properly photolithography, right? To me, it's the equivalent of, I have this filter LCD and I shine light through right way. Big powerful light, many times second. Psh, and it vapor. Big, not there now. Now turned into tiny atoms. Go away. But they don't like that, because that's literally what they're doing. It's like, I turned it into atom juice of the vapor. But it's like, why don't you just make it atom juice of the vapor variety in the first place, and then control it, as some like electromagnetic and electrostatic and, some basic capture, right? As I was, thinking about that, I was like, how do I better manage, like, nano-size particle distribution? I want to, like, capture nano-size particles of these, materials, right? But it's like, if it's in a vacuum and it creates an electrostatic field, then different densities will create different total charges, and I create my own atmosphere of those nano-sized particles, right? And so that means that this area, it's like, distilling, basically, from like, oil, right? Like, if you heat it up and then you get like, oh, I got the kerosene here, and I've got the diesel there, and and then it comes back down, right? But it's like, well, in a vacuum, and you happen to make it this about size, and you put a little electrostatic here, charge potential, and it'll grab it at various stages, because it's so light and in a vacuum, it basically just, hovers and stays more or less at its density with its others that are the same density. So you can capture that and use that. So I was like, well, I mean, wouldn't that be better in a large amount of ways? Of like making different quartz or silicon, or various glass substrate, right, that you can then layer on each other the right way with like light-based, inertial confinement, or basically a version of, make a connection of electricity at that one moment, and then light then increases the likelihood of electrical, ionic, or covalent bonding, right? So then that, because it's in a nice little area, you can then have it slowly clump the right way, and then move down the right way, and then have the right material around, atomic or nano size, and out pops transistor, big old chip clump, right? There's a big old, and then I'll just cut it, or if I don't need a big old, right, I get the big individuals, and I can combine them as necessary in a vacuum, get them close enough, hit them with a laser. It's like welding, basically, at that point. And that would be a lot easier. And no longer do I have to worry about the people that make the machines that make the TSMCs and more like viable. Because like there's only a few of them that like make those machines. As far as I'm aware, there's like one. They have a huge monopoly on it. It's like, well, this would be a lot better. Like I don't have to worry about only them and paying out the ass for that, you know, because that's super expensive. This would make it a lot cheaper. But you know, potato. It's mostly for light. You know, it's like a really fast way of making light bulbs that are extraordinarily cheap and inexpensive to make. Because I don't need them to be stupendously hyper accurate. In fact, we make LEDs all the time. You know what I mean? So usually it's this solution chemically, right? Instead of a vacuum, it's like solution. We do kind of a similar thing where we vibrate it. It's ultrasonic or infrasonic or whatever, and then they create their own distribution of density, right? And then like you can place in the right solution at that given area, and it stays there, while allowing for the right current to run through, and it collects and clumps the right way, and it precipitates out the way you need it to be, right? As it goes through, you can then filter that out and then have it run through the next one until eventually you get to this whole design that I'm talking about. And just, here's a chip that I already got from somewhere else, you know what I mean? It's basically the same thing, you know, it's an analog. We treat a chip like an analog. It's just going to have this delivery, right? But it's just going to modulate that delivery out as necessary to go onto the LED and the substrate pin set thing. So that way you don't have to worry about that producing so much heat that it's unbearable for the amount of light that you want. You know, like a movie set level of light that just heats up everything. I mean, these are literally like heat lamps at that point, which are insane to produce. Versus this, which would make it like way easier and way simpler to make that work. But you know, then that turns into, well, I can make a big photonic and regular transistor chip, you know, substrate that works all together, you know, as one big motherboard chip basically thing, right? And then pins are the standard input of electricity and output of electricity, and input of light and output of light. And then we have a brand new type of computational device, you know, and of course that's the denoising and all the rest of it that then heads towards the real big meat potatoes of the calculators, and then it goes and gets, you know, spread out as it typically. You can cool that usually a lot easier, and then it's sort of done, I suppose, at that point, because I mean, that's one hell of a big ass chip. But you know, it's a motherboard too. I mean, it's all in one. I mean, wouldn't that make it a lot easier? It's like I buy GPUs all the time, right? I don't. I don't have money. I literally have no money, so I never buy. But it's like you know, if you're a person that's like that, I'm inclined to go like, well, I buy GPUs all the time. You know, I have GPUs. They're all in one computer, basically. You know, you just stick them onto this thing. Why wouldn't I just do this? You know, I was like, so it's like, here's the substrate delivery power thing, you know, but that's the new motherboard. Right, can we stop calling it a substrate? It's just called a new motherboard. I don't know, I mean, it's just one thing. It's like it's soldered at that point, right? I know. That's the problem. Like, how do I convince people that it's like, no, you could just add things to that. You know what I mean? But then it's just soldered. It's like, I agree, but so is a GPU. I agree, but that's what a GPU is. You don't have any change to the GPU pin set, you know, or, you know, chipset, right? So I don't know, man. I don't know, like, why are you getting on my case about it? It was like, I want to put on different RAM motherboard, you know, or, you know, laptop, right, RAM or something, you know, for my GPU. I want a different GPU RAM, you know, stick it in my RAM and put my different GPU chip on there. Why don't we argue now, finally, for modular GPUs? Nobody's doing that. Nobody's arguing for this. So like when I hear like, well, it's not a motherboard, it's just a, and I'm like, it's the same, you know. Nobody's arguing for the GPU to effectively have something strapped to it, right? It's like, you could do that though. There's nothing saying that you can't do that. There's nothing saying that you can't just plug something into the GPU and then that's what your computer is, right? So I don't know. Like, it all depends. Like, they're all the same, but like the concept of like CPU, motherboard, and all that effectively works with any of them. Like a Raspberry Pi is effectively the same thing. Extreme together and add something to that, right? But it's like, no, I'll add the Raspberry Pi. And it's like, it all depends on what you want as the main thing, right? So it's not like a GPU though at that point, which is the thing. Although you could make it with a parallelization process. A lot of them, truthfully, at that point, that's more of like an APU, but then I don't really like parallelization for computation of various like light and movement of it through a given propagation because that's what it is. It has to go to this singular point of like camera, so it has to go and all those, and it has to calculate for all those different ways it did that. That's ray tracing, except it's also like the only way that it is that it calculates for any of these given different types of changes for these individual pixels that mean these voltages for your monitor to display something. This is really what that is. It's a chunk of various different like little puzzles in binary land that it saves. Like binary is like this little chunk means this basically, and it goes like this changed and this binary chunk is what has occurred, so deliver it like this, and that's the instruction. It goes on the other side, it goes to the cables until it goes to right, and it goes, oh, this voltage change modulation over there. That's all it's doing. Just FYI. But like they're like, no, and it then goes to a higher level, into a higher level, into a higher level, into a higher level, and then it goes, and then it was this actually. But that's a translator. See, like that's binary. What this really means for you to understand what the hell's going on. But it's like translate to and it's like this is some code that I know of actually, not binary. To then it also happens to go like, well, and this is what this language of this given if then of this given type of algebraic statistical, right? That then got translated all the way down into bleep bloop 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 bleep 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 blah bloop 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 bloop. Right, and that's all it really ever did. But we need to understand what bleep bloop 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 bleep 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 means. And we all have to be on board with it, which is why it's standardized, you know what I mean? Standardized programming, which nobody really thinks about that, but that's all an operating system is, or any given, like, development kit, for what it's worth. But it's like, I don't know what that really means. And it's like, oh, this is the bleep, bloop, bleep, bleep, bleeps that really mean, like, this voltage change for the light that you see. Now, imagine a screen, which is why this was really heading that way, would be using this, especially if you output some degree of light, an electrical change. That changes its degree, like in that fiber optic as a substrate, kind of like analog based, as it moves through that kind of like a breadboard in a lot of ways, but now it's an analog chip breadboard. Right, so it's like, right, now I can use both modulation of electromagnetic, but also modulation of various splitting, refracting, mirroring, so on, that then allows for it to go through the ray, that then outputs it as light that goes through, that then gets amplified both by electricity that's already there, right, but also amplifying properties of material. LED, right, is cool, sure, light goes through LED, nice, whatever. However, if I have the right type of light amplifying material that's passively that way, think night vision goggles, right? Well, they amplify and constructively interfere IR into natural light that we usually see. That's what the military now uses, right? Well, think similar. It's similar. So, like, you do that, they're fairly cheap. You run electricity the right way through it, it actually improves the degree of actual constructive and light amplification. Wonderful. You do that the right way, you get subpixels, because you can layer them. It's kind of like graphite stuff, which is what the military and others tend to use for very high spec stuff. Well, all that means is it's like graphite that effectively situates itself in between structures, and light then propagates through, and then it happens to pick up more light and constructively interfere into the light based upon the modulation of the electricity that's going through it. that means it then it changes both to its frequency, and what it means that it ultimately is that light that's coming to it was, for us, where it is, the frequency, the depth, and more. These are now subpixels that have subpixels that then have, the good old-fashioned bell curve stuff that then constructively interferes to itself as it both is somewhat entangled but then becomes no longer entangled. This is, that wonderful screen that would use that technology to improve efficiencies but also improve luminosity and directionality, viewing angles, right, and outright pixel density, as it is effectively a wall of light that's coming at you that then got interfered the right way to become a bigger, larger, almost think dome-like light that then diffuses out the right way that we see as, wow, that's a cool picture. And that's what all of them have ever done. But I digress. Then you have to get a little deeper into it, because it's like, well, it's also analog. It's like it always have light going through it. All right, that's one of my things that I wanted to do for my operating system development kits and changing how computers work and more. So that way it's more in line with how our eyes view anything. It's very analog. It's always updating. It's never endingly doing that. There's no and then it switched and then it switched. It's always doing it, right? So that actually makes it easier for us to calculate, because we only need a certain amount of change for any one area at any one point, which then allows for us to do sub-pixel changes at any given area. And meanwhile, that means we reduce the amount of CPU and GPU overhead. And while some of it is parallel, we're talking about chunks of parallel that start acting quite a bit more like a regular standard CPU that's more general, that we can use as necessary to change. And transistor basis has become a lot easier, although we are talking about now light-based, right, together with electricity. But that's also field programmable gates in that sense, because then that's the tube TV technology, electromagnetic field, that then allows for field programmable gate to be changed, and then this light goes there, and then frequency, blah, 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 blah. But if you make it all work together, and this is the shocking part, it gets better when all of them work together. But that's actually how our brains work. Electricity goes this way, looping brain, memory, this is a memory, it's a loop inside of a given area of connections for various neurons, right? Right. That changes how frequency, voltage of that given electricity gets modulated. But also that changes field collapse, of course, to various areas for ionic exchanges, which changes potentiation of how it is that you calculate based upon both memory but also various stimuli, light, and input. Which is an odd but very cool thing, right? That's how basically all of us work, but that's quanta phenomenon now. We don't like quantum phenomena. Penrose can't be right. Bye.